Hi guys, welcome to Learn Electronics Repair. I made a video very recently, all you need to know about TL431 to fix stuff. And if you watched that video, you'll know that the TL431 is a programmable Zenith diode, and we use these in a lot of situations and circuits, but one of the very common ones is in the feedback circuit of a switch mode power supply. So, for example, here we have a TL431. This is a little switch mode power supply out of an old satellite receiver. It does work. It's rather handy. 12 volts, 2.5 amps. I use this quite a bit when demonstrating things on the channel. So you see we have a TL431. That's this little thing here. Preamps, you can read that. And we have an OptoIsolator. And this circuit basically monitors the output voltage and sends a signal back to the controller on the high voltage side to basically say I need more or less power to maintain a standard steady voltage of 12 volts. I'll just draw that briefly and then we'll come to the point of this video. I explain this in much more detail on the All You Need to Know About TL431 video, but I'll just do it very briefly here so you don't have to refer back to that video to understand what we're going to discuss in this one. So the basic principle and circuit is that we have the output voltage rail of our power supply. Let's say it's a 5 volt power supply, but it could be anything else. I'll show you why. So we need to monitor this voltage here and tell the controller, the pulse width modulator, when we have 5 volts and when we have more or less, so it knows how to alter the pulse width modulation and alter the voltage being generated by the power supply. And the reason it needs to do that is because depending on the load that you attach to this, whether it's a mobile phone you're charging or something else, depending on the load and the current it's drawing, the power supply has to work harder sometimes to generate 5 volts and sometimes it has to work less. So if we didn't regulate it, the voltage would not be stable, or it would only be stable at a particular load current, and that's not what we want. So the way we do this is quite simple. We have a resistor coming to the OptoIsolator which has an LED in it. And then this goes to the TL431 we were just talking about, which goes to ground. And we can set the TL431 to turn on at a certain voltage. Naturally, this is a 2.5 volt reference, so it will turn on at 2.5 volts. If we want to turn on at 5 volts, we just use 2 resistors like this. And the ratio of these 2 resistors will set the point at which this turns on. If they're both the same value as each other, and the value doesn't particularly matter, at least not within quite a wide range, so if they're the same value as each other, you'll get a 5 volt reference. Okay, if you want a 12 volt reference, this resistor is higher and this one is lower. There's a page you can go to, TL431 resistor calculator. You tell it what voltage you want, you choose the value of one of the resistors and it tells you what the other one must be. So that's how it basically works, and there's a lot more detail on the other video, All You Need to Know About TL431 to fix stuff. Okay, I've plugged my other video enough now. So inside this OptoIsolator, we also have a photo transistor. This end generally goes to hot ground. This is not the same as safety ground. That's why we need the isolation. And this one will have probably a resistor coming into it to give it a bit of power. And it will go to the pulse width modulator on the feedback pin. And the idea is that when the output reaches 5 volts, this turns on, the LED turns on in the OptoIsolator, that shines on the transistor, that turns that on, and it sends a signal to this to say you've got 5 volts now. When you start drawing more power, the voltage here will drop a little bit. This will turn off, and this will say, oh, I need to generate more power. So it drives the power supply a bit harder to get back to 5 volts. Once it gets back to 5 volts, this will turn on again, and it says, I'm back at 5 volts. And that's basically how it works, okay? Now, this circuit you will find in all switch mode power supplies that need to regulate. But when I say all, there's always an exception to the all rule, yeah? And I'm going to show you one. Here we have a 48 watt USB power supply. Now there are at least 3 interesting things about this power supply. The first one is that it's rated at 5 volts, 3.5 amps. Now, watts equals volts times amps. And when I was taught to do this, 5 times 3.5 is 15 plus 2.5 is 17.5 watts. That is 17.5 watts. Now, clearly, whoever designed this can't do basic maths. They don't know Ohm's law and the power law, yeah, and they think 3.5 times 5 is 48. Yeah, that's the first interesting thing about it. We tested this on the electronics channel. This is the live stream every other Sunday with Detlef and myself, and amongst blowing things up and talking about theory and electronics in general, we also like to debunk this sort of junk which we buy from AliExpress. So that's the first interesting thing. This is actually a 17.5 watt power supply. Max, probably. Maximum, not average. Second interesting thing is this is clearly a LGBT power supply because it's like the rainbow flag. Yeah. Okay, colour's not in the same order, but does that matter? Yeah, it's still an LGBT PSU to us, so we thought you might like that, and I thought you might like that. And the third interesting thing, and this is what this video is about, by the way, yeah, is that this power supply XYZ3289 does not have an OptoIsolator or a TL431. It is isolated. You can see here there's a big gap on the PCB. So we have the mains input which comes into this side. Here's our little power connector that just kind of sits in there when it's put together. That's your power in, no fuse, no filter, anything. Yeah. So this side is your high voltage side. And what you actually have here, this is the pulse width modulator controller that's driving the transformer. That's your bridge rectifier. That is your large smoothing capacitor. How large is it? Not very large, that is for sure. 15 microfarads, okay. This is basically the entire input circuit. And then we have the big gap. So this is the low voltage side. So this thing here is in actual fact the rectifier diode on the 5 volt supply. This is the output capacitor that smooths the output from that rectifier diode. Okay, and then we have a couple of power LEDs and we have the output. So that's it. That basically is it. There's another smoothing capacitor there as well. You can see in fact that one is connected across the diode by the loops of it. I'm not too worried where that one's connected because it's not really relevant. In fact, actually, that capacitor and this capacitor, if you look at them, are in parallel. So you can see one end of this one connects to one end of that one, and the positive connects to here and also connects to here. Okay, so you can see all these rainbow USB connectors are in parallel. All the 5 volts are connected together, all the grounds are connected together, and yet interestingly this says 3.5 amps, 3.5 amps, 3.5 amps, like each pair can give you 3.5 amps. which probably comes to the 48 watts actually. 9, 10, 10.5 added together, yeah, 10.5 times 5. Oh, that's over 50 amps. Yeah. Unfortunately, this is just completely irrelevant because all these are actually connected across each other. So that's the circuit we have. Very simple. Rectifier diode, smoothing capacitors, output. Yeah, and this is the input. The only other thing you'll see on this, and you see this on every power supply, in fact there's one on ours here which does have the OptoIsolator. This capacitor is like this capacitor, and this is a filter capacitor. So what it does on both of these, it takes all the high frequency switching noise on the secondary and effectively feeds it back into the primary or high voltage side, which normally speaking would connect to ground. Yeah, it would connect to ground. Now this power supply has a ground stud there, so when it's fitted into whatever it came out of, it is grounded, and that grounds out all the noise. On this one, well, it doesn't really understand the concept of ground on the power side, so that isn't really doing a great deal. It's just sending the noise down to the mains wiring via the filter, which isn't there. So you can see when they built this as cheaply as possible, and if they could build this without having to fit a TL431, an OptoIsolator and 3 resistors, then they would do so, and they did so. So the question is, how does this regulate the output voltage? Because it does. We've had this with a load on the USB analyzer, and it does actually regulate the output voltage. How does it do it? Now there's a question. And of course, you've come to Learn Electronics Repair, because here you will find the answer. Or so you hope. But no, really guys, I will tell you how this works. Well, to understand how this works, we need to understand a little bit more about switch mode power supplies. And this applies really to all switch mode power supplies. I've discussed some of this before, but there's a little added extra coming now. So, with your switch mode power supply, you have your large smoothing capacitor. This is the 400 volt one, or 450 volt, and in front of this you have a bridge rectifier, which I can never be bothered to draw the whole symbol for, so plus minus AC AC, and your mains input, we'll put 240 volts, normally with the various filters that little thing doesn't have, but you really should have. But there we go. And across here we get about 400 volts DC. This is ground, but this is not safety ground. This is what's called hot ground, because basically inside here, which I didn't draw, are the diodes connecting between live and neutral and the various plus and minus. So this point here, via the diodes on one half cycle, is connecting to the neutral line, and the other half cycle is connected to the live line. So although this is our reference point, 0 volts for our test meter, it is not 0 volts for your finger. Okay, just mention that again. So what do we have then? We have a transformer, primary coil, which goes to a MOSFET. In our case, what we've actually got is a chip, pulse width modulator, and inside the chip is the MOSFET internally in the controller box, the little IC, the thing that's generating the pulses to drive this, and then this goes to, sometimes via a small value resistor to monitor current, but in our case I suspect there probably isn't one, and this goes to ground. So when the MOSFET is switched on, it pulls current through here. When it's switched off, the current collapses, or rather the magnetic field collapses, and it generates voltages in the secondary. Okay. and your secondary, diode, capacitors, and that's it out. In our case, this is now safety ground, and this is 5 volts. Okay, so that's how it basically works. Now this needs power to run. Yeah, needs power to run. And the power this needs to run, we'll call it VCC. This is the power supply to this chip. It's probably somewhere in the region 15 volts to 20 volts, something like that. Depends on the type of chip. But that VCC needs to come from somewhere. This can't do anything until it's got power. So the way this gets power is a little bit, not exactly complicated, but it's interesting. Okay, so from here we have a capacitor going down to hot ground, and we can either have a high value resistor here which charges this capacitor up when you put the power on. But in the case of this thing with so few components, and I'm just double checking now and I've spotted something I will mention to you. On this thing with so few components, internally inside this chip is a high value resistor going from the source of the MOSFET, going from the drain of the MOSFET internally to the VCC pin. Okay, so inside your chip, I'll just make it a bit bigger. You've got this. Hot ground. PWM. And then this is the VCC pin. Hot ground. And this resistor is inside the chip. Okay. And that resistor is high, maybe 1 mega ohm, something like that. 1-2 mega ohm. It's a high value resistor. This transformer coil you can see there goes to HT. This is your 320 volts or thereabouts. So when you first switch on, this doesn't have any power, it's not running. So the primary is just a piece of wire really. There's no switching on here, it's just a piece of wire. So the HT appears on this pin, 320 volts, and through this high value resistor it starts to charge this capacitor. And when the capacitor gets up to say 15 volts, this starts to run. Okay, so the VCC is powering the pulse width modulator part of this chip. This starts to run, it starts to pulse the MOSFET, and this starts to generate power. Now, the way the circuit is designed is that this high value resistor inside the chip can charge the capacitor up. Maybe takes a few seconds when you first switch on before it starts. But once the chip is running, it draws more power, more current than that resistor can supply. So the capacitor starts to discharge. This needs more power to run than this resistor can give it. So the capacitor discharges, it's feeding this. And after a second maybe, the voltage here will drop to such a point, let's say 9 volts. And this switches off. Okay, unless it gets power from somewhere else. Okay, when that happens, depending on the chip, the resistor will start charging this capacitor up again, and when it gets back up to 15, it'll start again, and it'll run until it just drops down to 9, it'll stop again. So this needs power from somewhere else. And the way to get the power, and I have shown you this before, you guys, is they have another secondary on the transformer. Okay, here. One end of this is also connecting to hot ground. Okay, and the other one via a diode. And quite possibly a resistor as well. Comes back to here, this point. okay, from the secondary. So what happens is when you start the power supply up, this charges 15 volts, it gets going, and before this can discharge back down to 9 volts, that winding via this diode recharges the capacitor, and now it can keep on running. That will keep them running, yeah. The beauty of this circuit, one of the things, is that if you have a short on the output, it'll also pull this voltage down as well, which will cause this capacitor to discharge, and this chip will switch off. Yeah. If there's a short here to start with, this can never get going, so you'll quite often hear this thing go chirp, 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 chirp. That's as it's repeatedly charging and discharging this capacitor, but it can't get going. So that's how the thing works. And this thing is called the auxiliary winding. And it not only powers that, but usually it powers the transistor and the OptoIsolator as well on the high voltage side. And you'll find that on all power supplies. How does this thing regulate? Yeah, it's not monitoring that. How does it regulate? Well, the way it regulates is actually really, really clever. What it does is this. It monitors the VCC. Okay, through a couple of resistors to ground, and it monitors that junction there, and this is feedback F, and that's how it's regulating. Think about it. If this winding had 3 times as many turns in the secondary as that one, when this reaches 5 volts, this will reach 15 volts. Okay. Now, depending on the ratio of these 2 resistors, if this one is twice the size of that one, so say we put like 20k in here, hard to draw, so we put a 20k resistor in there, we put a 10k resistor in here. When that reaches 15, at this point reaches 5. Okay. When you draw load, this voltage will drop due to the current, but also this voltage will also drop. Yeah, and because it's 3 times the winding, it'll drop by about 3 times as much. So it means that the voltage on the feedback will drop, and that's how it knows that the output is loaded and it needs to generate more power. That is exactly how it works. VCC, clear on my other diagram. Resistor to hot ground. Let's put a 20k, a 10k. Feedback. Crafty, yeah. Somebody said that was sneaky. Somebody said it was crafty. We talked about this on the live feed, but I thought I'd tell the rest of you who don't watch the live feed how this works. I would not call it either. I would say this is elegant. This is an elegant way of doing it. It may be that due to this capacitor, the regulation isn't quite as close as if we were monitoring this, but it's like close enough. Yeah, it's close enough, and that's how the power supply works. So guys, if you come across any power supplies and you've watched the all you need to know about the TL431 and you say, oh yeah, you told me all I need to know about from like when there isn't one, yeah, well, when there isn't one, that's how it works. And I'll just prove it. There's the little controller chip. I've just put the light on it so you can see it. So QC5783, that is the part number of the little pulse width modulator. Now let's find the data sheet. And here is the data sheet for this chip, with a typical application. And look, it looks like ours. So we have the high voltage part of the circuit there. This actually isn't using an internal resistor on here. Okay, it could have been, depends on the chip. This actually has a high value resistor here. Okay, and that charges this capacitor to put the initial voltage on here. When this gets high enough, say 15, this starts running, okay? Once that happens, this can't keep this thing running, it can't provide enough current, so this starts to discharge. But hopefully before this discharges down to say 9 and it switches back off, this secondary here, via the diode, actually charges this capacitor back up again and maintains the VCC, can keep on running. This is slightly different from the concept that I drew, where the feedback was monitoring from here. In actual fact, on this one, it shows from the winding a voltage divider, 2 resistors here that set the voltage on feedback. So it does work basically the way I said, slight variation, but you can see how this works. Somebody asked when we put this on the live stream, is there any isolation from the secondary and primary? Yes, there is, because this winding, this is the auxiliary winding. See the little triangle there? That's hot ground, hot ground, hot ground. I draw it like a little black stripe, but fair enough, that's all hot ground, and this is safety ground. So this winding and this winding are isolated from each other, therefore you still have isolation on the output. You will also notice this does have a current sense. It's there, you can see it, CS current sense, a low value resistor to hot ground. So let's just finally have a quick look around our PCB, see if we can identify where these components are. And here they are on the reverse of the PCB. So the 1 ohm resistor you see there, 1R. That one, 1R0, 1 ohm, that is the current sense resistor, okay. We have 2 resistors here, 4221, 1912. So these, if you look, one end is connected together, it's going to the feedback pin. These are quite accurate values, so 4220, 4.22K, that one, and this one, 191 and 2 zeros, so this is 19.1K, so these are quite accurate, they'll be close tolerance. The reason they are so accurate values is because we need to get the exact correct voltage on the feedback pin to make this work properly. And that is the diode, the one that is feeding from the other secondary, the auxiliary, into this. Okay, that's the capacitor it's charging. So there are actually all our components. The last one, this one, 365, that is 3, 6 and 5 zeros after it. So that is a 3.6 mega ohm resistor. And you can see that also charges the capacitor. So this is the initial startup resistor, and that will come from the mains. Yeah, so this is the bridge rectifier. You'll see another diode and this 100K resistor. That is basically a snubber network. It was on that little schematic if you wanted to see it on the data sheet, but this is basically just to prevent too much back EMF being generated from the transformer primary when you switch the MOSFET off. So guys, we can see now exactly how that has been implemented. I did mention it, so I'll show you again on the little datasheet schematic. That's that snubber network, that is the 100K resistor and the diode, and no doubt that capacitor is there somewhere as well. And there you go guys. If you watched the previous video, you'll know how to diagnose the feedback circuit, the TL431, and with this one you'll know how the thing works if it doesn't have the TL431. Yeah, so that's more stuff you can fix. Enough for me on this one then. I look forward to seeing you all soon on another Learning Electronics Repair video. Ciao for now guys.